So topic 2.3.1 is energy and work. There is more to topic 2.3, but I don't want to overwhelm you, so here we are. So topic 2.3 part 1, first of all, would start with you talking with a neighbor. What is energy? What does energy do? What are some examples of energy? You're watching this lecture video, so you've either already done that or you can think about it in your head. But energy is undefinable. In general, scientists can't come up with what it physically is, but we can categorize where it comes from, and that's what we tend to do. So types of energy that we have around us. We have gravity energy, nuclear energy, chemical energy, electrical energy, elastic energy, thermal energy, radiant energy, kinetic energy, internal energy, and mechanical wave energy. All of these have definitions that are in your textbook if you really need to know any of them, but we're kind of probably talk about them as we need them. So, types of energies. A model for thinking about energy, since it's undefinable, well, let's think about it like money. So money is, well, what is money? Money is something we use, and it comes in a lot of different forms, like dollar bills and pennies and nickels, and in other countries, it's other different even systems. But what is it? It's something we use. So that's the similar thing. So if I think about my money, I could either store it for later use, or I could transfer it to other people or other companies, other things when I need to. And so, for example, say I had $10,000. I know I have to spend money on things like groceries, the mortgage, taxes, insurance for cars and houses and stuff. And I can also spend it on fun stuff. But for the most part, I should be storing a lot of this money for things like I want to renovate a house, or I want to have savings for when I can't work anymore. So the 401k. I want an emergency fund in case I got into an accident or something, or if I had a health scare. And maybe for something fun that I'm saving up for, like a new car or something. So when I get a chunk of money, if somehow I magically won $10,000, I would use it for all these things. A lot of it would get stored for later use, and some of it would get used right now. So energy is similar. Either it's being stored for later use, or it's getting transferred between objects. So we're going to really distinctively talk about them in different ways. Potential energies that will get used or transferred later, and energies as they're being transferred. So let's talk about them. So potential energies that are inside of something that can be transferred through a force, are things like gravity, potential energy, nuclear energy, chemical energy, electrical potential energy, elastic strain energy, and kinetic energy. The definitions for all of these are on page 75 of your textbook, but again, we'll talk about them when we get to each one individually. Whereas when energy is physically being moved, we give them specific names like electricity or heat, electromagnetic waves or mechanical waves, or we say there's work being done. These are kind of names we use for when energy is being transferred. So pause and check your understanding number 1. This is an animation of a mass hanging out on a spring. And so as it goes through one cycle, you need to describe the transfers of energy of the mass. And so I know it's a little hard to look at that little graph, but if we think about what we know, well, gravitational potential energy comes from an object being some height above the ground. So when it started, this mass was up a certain height and it had gravitational energy. When I let it go, all of that energy is going to start to turn into motion because the force of gravity will pull it down. And I'm going to get some kinetic energy, but it's attached to a spring. And so the actual spring is going to start pulling back on it, and it's going to create some sort of a tension in the spring. It's going to create elastic potential energy in the spring. So as it's moving, I'm going to have kinetic energy, and that the amount of gravitational energy I started with is going to, some of it get transferred into kinetic energy as it's moving, but also elastic energy. Once it hits its bottom extension, or the max extension of the spring, will have as much elastic potential as possible, We'll have no kinetic energy because it'll pause for a second and turn around. And we'll still have a little bit of gravitational energy because it's above the ground, but it'll be less than before. When it starts to go back up, because the force of the spring will pull it back up, I'll again get kinetic energy as that elastic energy transfers into motion. And I'm going to start gaining more gravitational energy as I go back up to the top. Now, if you sit and watch the spring for a long time, you'll notice it won't get all the way to the top because throughout this motion, there's going to be air resistance stealing some energy away through heat. And so that is kind of what's going on here. And you can kind of see it with these little bars. We have the gravitational energy, which is the dark blue one. We have the light blue, which is elastic energy. And you can see it grows and then diminishes. We've got the green, which is kinetic energy during motion. And we have this little red one, which is the thermal energy leaving the system. But one important thing to know about all descriptions of energy, which is something you'll do on your IB test, is that the energy can't be created or destroyed. It can only get transferred from one form to another or from one object to another. And so energy is undefinable, but we can categorize where it comes from and how it moves. And we'll keep talking about this throughout the lesson. If you do need a definition for energy, one way to talk about it is that when energy is transferred, it gets work done. So by definition, an energy transfer or a change in energy is equal to work. I think that equation's somewhere in your textbook, but it's not in your data booklet. It might be in your data booklet. We have to double check. So, energy transfers, gets work done, or accomplishes tasks. So for example, when I lift up a box or something, I'm using my muscles to apply a force upward. This force requires me to have some sort of energy that I expend or I transfer into the box's height. Okay, and so I'm going to use my chemical potential energy, which comes from all the food I ate and stuff, to turn that into gravitational potential energy of the box. How much depends on how far I lift, and the further I lift, the more work I physically have to do. So this leads to the next point. Work is applying a force through some sort of distance. And so the equation for work, which is in your data booklet, is force times distance. But be careful. That's not a multiplication sign. Force is a vector. So that is a vector multiplication, which, since we don't teach calculus, I can't teach you. But in general, what this means is that I won't get work done unless the force is in the direction that the object moves. So I've got a funny example. Here we got Peppermint Patty, and she is pulling and pulling and pulling on the door. But because the door can't move that way, she's wasting all of her energy. Whereas Charlie Brown comes, he pushes the door the correct way, and he gets work done on the door. He accomplishes his task. So in general, the direction matters, since force is a vector. If you could apply a force, but it's in a direction the object can't move, you can't transfer your energy into the object. Rather, you're going to just get frustrated and create lots of heat and flustering and internal energy and thermal energy. So the actual equation in your data booklet is this one. Work is equal to force times distance times the cosine of the angle between the two. So force, which is a vector, basically gets relegated to the force in the direction of the distance using this cosine angle. So for example, say you wanted to move this block 10 meters, but you can only grab it with a rope that's angled at 20 degrees to the ground. How much work would it take to move it if you use a force of 10 newtons? Well, the force is in the wrong direction. So the force, it's not going to be 10 times 10, 100, what we call actual joules of work. It's going to be less than that because I can't apply all of it to the direction I want to go. So I'm going to get 10 times 10 times cosine of 20. And so the work, really should have pulled out a real calculator for this, is going to be 100 times the cosine of 20. Which is just 93 joules. So I used a new unit there that I forgot to mention in the equation. So work is measured in joules. Energy, which is going to be newtons, multiplied by meters, multiplied by an angle, which goes, there's no units on that after a trig function. And so a joule, which is the unit for energy, a capital J, is equal to a newton times a meter. And this energy was actually discovered, this relationship about forces and meters was discovered by Henry Joule, which is why we call it a joule. And so a joule is a newton meter because it was his way of comparing physical force and how much work it can accomplish compared to heat and how much it would take to boil water. And there's a famous experiment that he did back in the day where he dropped a weight that spun a windmill and it heated up some water, and he equivalated the gravitational energy and the distance it moved to the actual heat created. And so he was the one who discovered that energy in any form is just energy. So we honor him with the joule as the unit. Let's do one more pause and practice while we're here. So this is from the IB textbook. The pram in figure 2.99 is being pulled with a force that is not in the same direction as its movement. So we want to calculate the work done when it's pulled 90 centimeters to the right with a force of 36 newtons at an angle of 28 degrees. So go ahead, pause and try this. Okay, so you're probably unpaused and you have your answer, but I'm curious, did you remember that I said that a joule is a newton meter? So you need to have the distance in meters? Because the correct answer should be 28.6 joules. But if you're rounding, 29 joules to 2 sig figs. So if you did this correctly, make sure that you have, if you didn't, check that you were in meters and that your calculator is in degrees. So a problem with calculating work. What if that force isn't constant? Most people struggle to maintain forces because our muscles just can't do it. And so many forces, especially reactional forces, like from a spring or a surface, they vary with other factors like the weight of the object or how far you have pulled something. So for example, springs are more resistive the further and further you pull them because the bonds between all the little atoms are getting stretched out. And so the further you extend a stretchy material like a spring, the more it's going to resist you. So that force grows as the extension goes to the side. And this is actually a specific force called a spring force. And depending on the material you're using, it's might be a lot of force or not a lot of force. You've all had very stretchy things and not so stretchy things. And so a scientist called Hooke figured out that if you measure the extension compared to the force, there's always this constant that goes with it, which is called K. And so the force of a spring is K times X. And so if we want to know the work done by a spring, which actually is used in a lot of engineering stuff, the work should be the force times the distance it's moved through, but it's always different. And so what can we do? Well, remember, we're talking about force multiplied by distance. And so if I want to know the total work that was done here, it's just the area underneath. It's going to be height times width, but of course, because it's a triangle, it's only half of that value because of the constant change in the spring. And so a side note, all materials have what we call an elastic limit. And so a point where if you pull beyond, you're going to start to actually break the bonds between the molecules and it won't go back. So if you've ever played around with like a rubber band or a string or something, at some point, if it's been used too much, you start to lose that stretchiness because you've broken the bonds between materials. And this is called strain of an object. And so when the strain becomes too much, it breaks. And so engineers like to use stress strain graphs to kind of watch their materials and figure out when they fail. And so this is a stress strain graph that's from your IB textbook. And so stress is just a measurement of how much force you have on an area of an object. And the strain is how much the material has changed compared to its normal length. And so when you compare these two things, you can actually see that for most objects, they behave really linear for a while. And then you start to get some sort of damage, and eventually it'll snap in half. And so this is a stress strain, and this is a part of what scientists do. They measure material science, how the material behaves. And so why is this all important? Why am I making you do this? Well, it is going to help us predict a lot of things. And so, for example, when we start to measure a bunch of the energies, you're going to be able to figure out things if you know heights and speeds and stretched distances of objects. So, for example, if I drop a ball, we know its gravity energy comes from the force of gravity and how high up it is. So I have my force of gravity, mg, and the distance that I have moved the object through, which is its height, and that'll give me how much energy is in the object. And so if that's how much energy I have due to gravity, when I transfer it out, this is the amount I'm going to transfer out. And so I could transfer it into kinetic energy of an object. And so pause and check. Can you do that? Can you do that equation? What is the mass times the force of gravity times the height? If you got 128 joules, good job. Again, if you were using sig figs, because you only got 2 sig figs, it would be 1.2 times 10 to the 2. So that's how you would do potential energy. Kinetic energy, this one's a little harder. So since work is force times a distance, but we also know force is from Newton's second law, mass times acceleration. And we know accelerations and velocity squareds and distances and stuff with our other equations. When we have an object like a ball that's dropping, well, if u is 0, this goes away, and s could just be written as v squared over 2a. And so if I plug this in for distance and I plug force in for here, the work of an object that's moving is just 1/2 times mass times velocity squared. Try and do that. Try and plug it in, see if you get the right answer. But you probably saw this in 9th grade, so you probably know kinetic energy is 1/2 times mass times velocity squared. So let's check it. That same ball, it had 128 joules of energy, and it's now about to hit the ground. How fast is it going? Well, if I know that the kinetic energy is 1/2 mv squared, and all that gravity has just been turned into kinetic energy, I just have to multiply by 2 and divide by the mass. That's the velocity squared, so I need to do a square root of it. And so it'll be going just under 9 meters per second when it hits the ground. Last but not least, another thing you're commonly going to calculate is potential elastic energy. So from like springs that are extended. Again, I told you that the force of a spring is K times X. K is just a constant. It's called a spring constant, even if the object is not a spring. Just any stretchy material has a spring constant. And so from this one, the way to figure it out, I told you work is the area under the thing, but since it's a triangle, it's 1/2 x times K times X squared, because X times KX is KX squared, and it's half because of the triangle. So if you need to find the elastic potential energy, that's how you'll do it. So the spring constant of this spring is 0.43 Newton meters, And if it's stretched to a distance of 4.5 meters, how much elastic potential energy does it have? Well, we have X and we have K, so let's do it. 0.5 times 0.43 times 4.5 times 4.5, 4.35 joules of elastic potential energy. Oh, except that was in centimeters. Whoops. My bad. 0.43 times 0.5 times 0.045 times 0.045, we're talking about 4.3 times 10 to the negative 4 joules. Not a lot. But some springs obviously have much bigger stiffnesses than others, and in general, springs can only give you so much when they're by themselves, which is why for most stretchy things that use springs, there's a lot of springs underneath. So this is your 2.3 part 1. If you need more, read pages 69 through 88 for more details and examples on all of this, some more practice problems, and good luck.